Alright, very important video here. Let's see if I can do it justice. Alright, so conservation of energy. Um, First, let me start off by defining mechanical energy. Mechanical energy is the total amount of potential energy and kinetic energy in a system at a given time. So, for example, let's say, let's use a pendulum, basically a thing that on a string that can swing back and forth, back and forth, back and forth. You're getting very sleepy. AP Physics is your favorite class. AP Physics is wonderful. Wake up! Anyway, so a pendulum, right? And you can imagine a pendulum being held up here by someone's hand, maybe yours, and you're just holding it, right? So it has some gravitational potential energy. It has the potential to change its configuration and drop in height. But if we're holding it, it has no kinetic energy. It's not moving. So we could say that the mechanical energy, or the total amount of energy in the system, is made up solely of the potential energy here. So let's just say it has 10 joules, for example, nice number, 10 joules of potential energy and 0 joules of kinetic energy. So we let go, right? It drops. It lowers in height, so it loses gravitational potential. But where does that potential energy go? It, due to conservation of energy, it doesn't disappear. It's not destroyed. It actually stays in the system, but it changes form from potential to kinetic. And so as it speeds up, because kinetic energy is the energy of speed, essentially, 1/2 mv squared, then as it speeds up, the potential energy converts into kinetic energy. So down here, there would still be 10 joules of energy in the system, but if this is as low as the system can go because the string can't allow it to go any farther, then all of the potential energy is gone. It has no more potential to drop any farther, and all of the energy is in kinetic energy now. Likewise, if if it continues on up the other side, but it hasn't reached the same height as before, it may only have 2 joules of gravitational potential energy, UG, which means due to conservation of energy, it would have to have 8 joules of kinetic energy to add up to 10 total joules of mechanical energy. So that's sort of a nice simple example of conservation of energy introducing mechanical energy. And you'll notice the energy in the initial state, which is up here, equals the energy in any final state, whether it's way at the bottom or somewhere halfway in between or midway in between. The energy is equal, 10 joules, 10 joules, 10 joules, 10 joules anywhere. So that's saying that this energy is conserved as long as the system is closed to outside influences. So if there was wind or air resistance or some other thing that was brought into the system, then that may change. The mechanical energy may change. But the problems we deal with, we keep them in a closed system. Some other examples, like someone going down a spiral, like water slide at a park. You might be asked to try to figure out their velocity down here. So you might be thinking, oh, kinematics is gonna be hard because they're always changing direction. What's that circular? Ouch, right? But if you think of it in terms of energy, and you start at a rest up here, you're a certain height up, right? And not only that, not only are you a certain height up, but that height is a vertical distance. None of this sideways motion matters. And so with that height, you can figure out your gravitational potential energy up here. And even if you don't start at rest, and you have some kinetic energy up here, that's still your total mechanical energy. That stays the same down here. So whatever you've lost in terms of potential energy, you've gained in terms of kinetic energy. And this can go with a spring type problem. So if you have like a spring here on a ramp connected to something and a block on there, and you let go, and of course gravity pulls it down, right? So now we're mixing U potential energy in terms of gravity and potential energy in terms of spring. Doesn't matter. The total mechanical energy, which in this case would be UG and US and KE, remains the same. So that makes solving these problems very straightforward and simple, but the tricky part is there is no set equation. Each particular instance depends on what's in there. Is there a spring in there? Is it gravity playing a role? What are the speeds? Whatnot? So the conservation of energy equation that you make, in other words, you can make this into equation, right? Mechanical energy initial equals mechanical energy final. This is sort of your basic equation. That's what's always the same. But what makes up your mechanical energy changes based on the situation. So it could be a little tricky at first, getting used to dealing with that, but it's not too bad. So I'll as I do sample problems, or when I do sample problems, you'll see better examples of this. But for the rest of the video, I kind of want to talk about these potential energy curves. You don't have any problems in your homework that deal with these, but oftentimes these type of questions are seen, especially in the multiple choice on the AP exam. So it's worth talking about potential energy curve. So what you see here on these two graphs are potential energies on the y-axis and configuration, or essentially location, displacement, whatnot, on the x-axis. And so for a given system, a potential energy curve might look like this, meaning if you're at this location, you'll have zero potential energy. So this might be at the ground height, ground level. And so for this particular system or situation, we have a very interesting looking potential energy curve. So what else you can analyze from this is, for example, the whole restoring force. You can see very quickly that this type of system, you can restore yourself back to a certain situation. It's easier to see down here, where you can even imagine a ball in sort of a bowl. This is like a bowl shape, right? So if you take a ball here and let go, it's going to roll down the hill and go back up this hill, and it might oscillate back and forth. Or here, if you start here, the ball might have enough energy going down here to go up and actually go over this hump and continue on. That's sort of a visual analogy. That's not really exactly what this potential energy curve is. Not a bowl or anything that a real ball could roll down. And then this line here would be the mechanical energy of the system, and that can change depending on the initial conditions. Here the mechanical energy has you start off with 4 joules of mechanical energy, whereas here you start off with 5. So if you start off with 5 joules of mechanical energy, you have enough energy to make it past this sort of plateau. So if you have, let's say, if this is all just gravitational potential energy, if you let go, then the object can decrease in potential energy. You can think of it as falling, increase in kinetic energy. We're going to have our maximum kinetic energy here because we've lost all of our potential energy. But then we can go back up and gain more potential energy, losing kinetic energy. But based on the system, if we're at this position, we can't go any higher, and so, or we can't. Anyway, we can't gain any more potential energy. But you take the same system, and if you decrease the amount of mechanical energy in the system initially, then that may limit your ability to move around in the system. So if you only start off with, say, 3 joules of mechanical energy, and initially all of that is in potential, and you let go, then you'll lose your 3 joules of potential energy. Down here you'll have 3 joules of kinetic energy, but then you go back up, and you'll never be able to make it over into this part because you'll have gained just enough potential energy so that you lost all of your kinetic energy here. You're at rest, and you can't go any farther. Um, so do some thought experiments. Think about these for a bit. That's a lot of words for a short amount of time, especially for never seeing a graph like this. But let me just leave you with one more point, and that is the relationship between energy and force. You know that the derivative of energy or work is another way of thinking about it, is force, or vice versa. The integral of force is work with respect to displacement or position. So this would be your force graph. So what type of system could possibly give you this potential energy curve? It is a system where you have this type of force at each of these positions. So I have no idea what this could be. No idea. But it could exist where if you're at this position you experience a positive force like this, whereas if you're in this position you experience a negative force. And so you could go and basically say you have the maximum positive force here, so that's going to be pushing you in the positive direction, and so that's why you want to go this way, because the positive direction is that way, negative direction is that way, and so if you have a positive force it's going to be pushing you that way, so you're going to be going down, sort of down in potential energy, gaining kinetic energy. But suddenly you hit here, you have no force, and so that's you no longer experience a change in potential energy unless you move away from here. And so if you do continue on over here, notice you're slowing down. You'd actually, if you started off here, you would actually want to go back down this way. That's because you have a negative force pushing you in the negative direction. Yeah, so you might want to watch this segment a few times because I really did a lot of talking, and these graphs there's a lot going on here, so don't feel bad about watching the last 4 or 5 minutes multiple times until light bulbs click. But in the spirit of keeping videos short, I'm going to stop this now. Oh yeah, don't hesitate to ask me clarification questions in class or via email about this. It is important, even though you're not going to see any problems specific to graphs like this in your homework. All right, so until next time.